Okay, thanks. So let us begin with today's presentation. So today we'll be dealing with the tutorials on the week 8 contents for Introduction to CFD course. So the week 8 contents are mainly on numerical solution of 2D incompressible Navier-Stokes equation. So I am Sumant. I am a PhD research scholar in Department of Mechanical Engineering at IIT Bombay. So coming to this week's content, so there are three main things which are present in the title of this week 8. 2D incompressible Navier-Stokes equation. So if we kind of split this particularly into three parts, one is the 2D. So in many of the flow situations, the flow becomes 2D. That is, for example, when you are trying to solve like flow in just a channel, for example, you can take a flow in a duct. Okay, so in this particular example, what you can see is that if you divide this whole domain into in different xz planes, for example, if this is x and this is z. Okay, so if you are dividing the whole domain into different number of xz planes, you will see that the flow remains same. That is, the flow velocity pressure remains same in these different xz planes which you consider. So in such situation, we can approximate the flow to be two-dimensional in nature. Okay, so this is just one example. This is just a flow in a duct, or you can say flow in a rectangular channel. Okay, so this is one example. The second example you can consider is the flow in cavities, and these flow in cavities are mainly investigated for industrial application, like for example paint manufacturing industry, for wherein they kind of take this uh, three-dimensional cavity. Okay, this is just something like a cube or a cuboidal shape. Okay, so in this, basically what happens is that fluids are mixed with some particles, chemical particles, to kind of get the paint. Okay, and different colors. So what happens is that a conveyor belt is usually moved on the top surface. Okay, and then basically fluid moves in different planes, and then mixing with chemical components happens. Okay, but what happens is that again, if we take xz plane here, okay, x and z, and different, if we take different xz planes, okay, this is one xz plane, the second xz plane. Many a times when the conveyor belt moves very slowly, we see that the patterns, the flow patterns and the velocity, pressure remain same in all these different planes. Okay, so this particular type of flows can be studied by just using 2D equations, by ignoring the velocity in the other direction. So for here it is y direction, so we assume that there is no flow, there is no cross flow which is happening. Okay, if we consider a flow in a tube, okay, in this case uh, we cannot exactly use the 2D equations, because what happens is that you all know that a parabolic kind of velocity is developed, wherein the flow from the like the wall, which is for example circular in nature, so the flow tries to come to the center of the channel. Okay, sorry, center of the tube. So there is some velocity in this say the w direction also, at least if you are not taking fully developed at the inlet, if you are just taking a flat profile at the inlet. So that is why you cannot call it completely a 2D flow. Okay, although we can make some axisymmetric approximations and come with the 2D equations in polar coordinates. But if you take only the Cartesian coordinates, this x, y and z, there the flow cannot be 2D. Okay, but whereas in the first two cases which we discussed, okay, the flow can be considered to be two-dimensional in nature. So I hope that is understood. So the second part is incompressible. Okay, 2D incompressible Navier-Stokes equation. So second part is incompressible. So we have to always remember that we are talking here about incompressible flow, and incompressible flow is different from incompressible fluid in a sense. So incompressible fluid basically means that the fluid's density itself does not change with respect to time and space. Okay, so for example, if we have a one particular whole domain, so for example, as I took earlier, a duct. Okay, so this is the whole duct in two dimension. Okay, so what happens is that the whole fluid, okay, it has a particular density and it does not change when some external pressure is applied on that fluid. Okay, and it might not be in flow condition also, it might be in a static condition, that is the fluid might be stagnant. Okay, even then if we apply some pressure on this, okay, then its density or the volume, it does not change. Okay, so that is incompressible fluid, it is a property of that fluid. Okay, but if we consider incompressible flow, the game is completely different here. Okay, so here what happens is that we take a control volume. Okay, and in that there is some fluid packet. Okay, assume that there is a fluid packet. Now when we trace this with respect to time, we assume that the density of this packet does not change, okay, over the time wherever it moves. Okay, this packet wherever it moves, but you can have a variation in density across the domain. Okay, if this is your whole geometry, here density might be rho 1 and here the density might be rho 2, but we assume that the flow is incompressible because this packet which we consider does not change its density over the time when it flows. Okay, so that is the main difference between the incompressible fluid and an incompressible flow. And these conditions where there is a change in density mostly occur in multi-phase flows. Okay, so you have a separate domain of CFD wherein you kind of get this multi-phase flows and the densities are different. Okay, but still we consider incompressible flow assumption. Okay, so in a pipe, if we consider at the inlet, if we just take a constant velocity, then what happens is that initially the flow tends to move away from the wall in all the directions, in from all the directions. That is, if we take in a tube, okay, if we have this kind of tube wherein we have this particular wall, so this is the top wall, bottom wall, and this is side wall. Okay, just assume that now the fluid in this particular case, okay, when it enters from the inlet, it tries to move to the center from all the directions. Okay, even from the top bottom wall and even from the side walls. Okay, so that is why the flow becomes three-dimensional in nature. Okay, but there is a trick that we can use, axisymmetric approximation, that is we can convert the equation into polar coordinates and then we can use the 2D equations to solve. But if we take xyz coordinates, it is 3D. Okay, but if we are converting into polar coordinates, then the flow can be considered as two-dimensional, because there the third dimension in polar coordinates is a rotational velocity, that is the theta. So that will be zero, the flow does not rotate, right? So only the flow will be in r and z direction there. Okay, r basically means from the center you take the radial distance, okay, in all the directions, so that will be the r, and z, that is the axial direction. So there only two coordinates will come into picture, There you can say that you can use 2D equations, but the equations will be different. But if you take the Cartesian domain, this is the like x, y, z, okay, so there the flow will be three-dimensional. Okay, I hope that question is answered. Okay, so yeah, so we were talking about 2D, 3D, and then we tried to understand what is the difference between incompressible fluid and incompressible flow. Okay, incompressible fluid basically means that it is just a property of fluid wherein if we consider even the whole fluid, okay, its density does not change on the application of pressure. But when we come to incompressible flow, we only take one packet of fluid which we want to study, and when it moves with respect to time, when it moves in the domain with respect to time, its density should not change. Okay, so that is mainly incompressible flow. But we can have variation in density across the space for an incompressible flow. Okay, so I hope these two things are understood now. So let us come to the third aspect, 2D, incompressible, and third is Navier-Stokes. So basically, uh, we had to derive some equations which can physically model the flows. Okay, so basically which could actually give us the values of velocity and the pressure in a domain for a fluid flow. Okay, so we mainly used the mass conservation, momentum conservation. Okay, we knew that the mass and momentum needs to be conserved, and along with that if there is a variation in temperature, then the energy also needs to be conserved. Okay, but we did not have a set of mathematical equations. So there were two scientists, mainly Navier and Stokes. They came up with a mathematical equations, okay, for conservation of momentum and conservation of mass. So that is why these equations are named as Navier-Stokes. Okay, these are the names of two scientists who came up with mathematical equations. Okay, mainly we will deal with mass and momentum. Energy we can deal it with in a later sections. Okay, so these are the two physical laws which are being used: conservation of mass and conservation of momentum. From this mathematical models are obtained. Okay, I hope this is clear. So we have touched upon all the three aspects: 2D, incompressible, and Navier-Stokes Navier-Stokes equation. So the other major thing which we have to look at is the assumptions which are involved in this Navier-Stokes equation. Although they are the conservation of mass and momentum, so mainly what is assumed while deriving these equations is that the uh, the domain we are considering the physics to be in continuum. Basically, what does that mean is that see, whenever we try to divide the domain into small number of control volumes, okay, in finite volume method we try to divide in terms of small control volumes. Okay, when we derive these equations, the mass, momentum, and energy, okay, on these control volumes, okay, we assume that whatever this length is there, na, the length along x direction, delta x, delta y, and delta z, these deltas are much greater than the mean free path of the fluid molecules. Okay, so wherein they collide with each other. Okay, that will be in nanometer scale. Okay, usually micrometer or nanometer scale. Okay, so the deltas which we consider in our fluid flows, they are much greater than this mean free path of the molecule. So that is what is assumed, and based on that we come up with the equations. Okay, why this is required is because when we go very close to this mean free path of the molecules, the physics itself is different there. We need to consider different types of collisions, due to which different diffusions come into picture. So our Navier-Stokes equations will not be valid in those cases. and a separate physical models needs to be done, which are much complicated. Okay, so and in many of the practical situation, this condition holds true. Okay, that the delta is much greater than the mean free path. Okay, so this is the main assumption. There are many other assumptions, but I wanted to highlight mainly on this assumption. The other assumptions include that the material is like homogeneous in nature. Okay, all those things are there, but this is the main continuum approximation. Okay, so finally, when we land up with these assumptions, we'll end up with for 2D flow, we'll end up with one mass conservation and two momentum. Okay, two momentum x and y direction. Okay, so can you write down on the chat box what are the main challenges which are involved with these equations? Can you directly solve them? If you cannot directly solve them, like your Laplace equation, you had delta square t. Okay, you were able to form the linear algebraic equations with delta square t, and you were able to come up with a solution for this case. Okay, what are the main challenges? Can you write down on the chat box for this mass and momentum conservation? See, mass conservation equation consists of velocities, okay, only velocities. Whereas in the momentum conservation equation, you have velocity as well as pressure. But mainly the momentum conservation is applied for velocity calculation, okay. Yeah, the equations are coupled, that is, they are connected to each other. That is a good point. Okay, that is one challenge which we face. The second challenge which we face is that there is no explicit equation for pressure. Okay, so x momentum gives us an equation to calculate x velocity. Okay, u I will call it as, whereas y momentum gives us an equation to calculate, okay, v, and the mass conservation doesn't have pressure at all. Okay, so only u and v it involves. Okay, so we do not have an explicit equation, okay, for pressure. Okay, that is challenge number 1, p equation. The second challenge is they are coupled. Okay, that is they are connected. Okay, the third challenge is that they are non-linear in nature and you cannot just use your iterative schemes directly. Okay, we have to come up with linear algebraic equations, right? The algebraic equations need to be linear to solve them. Okay, although you can solve non-linear, but that is a quite a complicated task. Okay, so we usually have in the advection term u du by dx term, okay, in the x momentum, say. Now you can understand when we do the discretization, you will end up with u square. Okay, ui square or ui into ui plus 1. Okay, so basically u square comes into picture, which makes the equation non-linear in nature. So in order to avoid this non-linearity, what we do is that we lag this by one iteration, or if we are doing transient simulations, we take it as a previous time step. Okay, when we are going with n plus 1 for this particular spatial derivative, we lag it by one time step or by one iteration. That is the way in which we linearize it. Okay, now the main other challenge is the fourth challenge, uh, that whenever you go with our normal control volumes and the grid arrangement, which is called as collocated grid arrangement, wherein you have this pressure, x velocity, y velocity at the center of this control volume, you will end up with staggering problem. Okay, which I will explain with one of the problem in the tutorials. Okay, we have a problem which can exactly tell more about this. Okay, so in order to avoid this, we have come up with a different type of grid arrangement. Okay, which is called as staggered grid arrangement, wherein we locate pressure at the center of the control volume. Okay, but we locate the x velocity at the, say, east face, and we locate the y velocity v at the north face. of this control volume. Okay, so in that way we were able to avoid uh, the pressure velocity decoupling problem. Okay, so let us begin with the tutorial problems. Okay, so the first question is based on the vorticity transport equation. So vorticity transport equation is mainly obtained in 2D flow in order to remove the need for pressure. Okay, so as I told, there is no explicit equations for pressure. So we want to somehow get rid of pressure so that we can have two equations, two unknowns, solve them. Okay, that is very easy to do. So that is why we come up with vorticity stream function. First we try to calculate the vorticity stream function through these equations, and then maybe we can convert it in terms of velocities. Okay, and if we need pressure also, we can do some adjustments. Okay, so the 2D vorticity transport equation can be expressed as which of the following options. Okay, so C, option number C. Are there any other possibilities? One is you are telling option number C. Okay, so let us try to see it, how the equations are from the beginning. Okay, so usually it is say in an unsteady state, dou omega by dou t plus you have u into dou omega by dou x. Okay, plus v into dou omega by dou y is equal to nu, that is the kinematic viscosity, into Laplacian of omega, that is dou square omega by dou x square plus dou square omega by dou y square. Okay, so these are the equations. Okay, in a scalar format, in a non-conservative form. Okay, so this whole thing, it is usually called as material derivative. So whenever we deal with the Eulerian approach, which we usually do in CFD, we fix our control volume at one particular point only. Okay, so we need to also account for the advection of these velocities across the surface. Okay, so that is why this extra term comes into account, the advection term, and then this whole thing is called as the material derivative, that is the total change across time. Okay, so if we had followed Lagrangian framework, okay, wherein we move with a fluid packet, okay, we move with this fluid packet, then this would have been absolutely not necessary. Then this transient term, that itself would be equal to the material derivative. Okay, so this is just to account for the movement of the fluid, so that is why this term comes into picture. So this whole thing is called as material derivative, and then you have nu into Laplacian of omega. Okay, yeah, because omega is transported by flow. Yes, so basically we have that equation. Okay, so mainly option number B can also be correct. So it can be written in terms of material derivative. Then definitely if we try to convert it into a vector format, okay, so then we can decompose this particular advection term which is there here. Okay, this particular advection term in terms of vector format, we can decompose ui plus vj cap and then the gradient. Okay, so in that way, if we write it, then it will become the option number C. So both option number B and C are correct. Okay. No, B is also for Eulerian. Okay. So if we take Lagrangian frame of reference, this advection term itself will not come into picture. Okay. So U into dou omega by dou x plus V into dou omega by dou y will never come in the transport equation. Okay, so if we are considering a Lagrangian approach, this term itself would have not come. Okay, since we are considering Eulerian approach, along with the local acceleration, we have to also consider the acceleration of the control volume. Okay, that is from the flux which we consider of x velocity and y velocity. So this is in Eulerian format only. Okay, this is not in Lagrangian format. I hope I have answered your query. Okay, so this is in Eulerian format only. Okay, even the option number B. Okay, if it was in Lagrangian format, okay, this second term and third term, that would have not appeared at all. Okay, so option number B and C both are correct. So let us look at second question. The dimensionless vorticity and stream function can be written as, how can we write basically the dimensionless form of vorticity and stream function? Okay, so that is particularly the question here. So if we see, for example, the vorticity, okay, we know that vorticity can be written as, for example, in the z direction, dou v by dou x minus dou u by dou y. So if we see the dimension, okay, it will be just velocity divided by the length. Okay, so dimensionless, that is why I am marking as star. Okay, it corresponds to the dimensions of this v star by x star. Okay, that is the way in which we can dimensionless form we can write. Okay, so this is nothing but conversion into primitive variables. Okay, because we know the non-dimensionalization of velocity and the distance. Okay, but we do not directly know the dimensionless form of this one. That is why this exercise is being performed. Okay, so now if we substitute this v star and x star in this particular equation, okay, for omega star, what we'll end up with this is this omega star, we can write it as v by v u infinity, that is the non-dimensionalization of velocity and the non-dimensionalization of the distance. L is the characteristic length and u infinity is the free stream velocity. Okay, so then we come up with the vorticity into basically length divided by u infinity. Okay, so this is the dimensionless form of vorticity. Now similarly, if I write the equation for stream function, can you write the dimensionless form? So I have already written it here. Okay, so stream function, because what happens is that, let me just explain it. Because see, you have u is equal to d psi by dy, right? So basically you can write d psi is equal to u into dy. Okay, so that is why if we take the dimensions into account, okay, which implies that xi star will correspond to v star, the velocity, into the length, okay, x star. So that is why I have written that particular equation. Okay, okay, so basically, if you see now, what should be the next step which we have to do here? We have to come up with a uh, dimensional psi also, similar to how we have done here. We wrote that v by x will be omega. Okay, so can you write on the chat box now what it should be now? The next step, u infinity and v l will be there anyways. Okay, we have to relate the dimensionless stream function with a dimensional form. Okay, so we can just write this v into x into as a dimensions of stream function. Okay, so the dimensional stream function psi, so v into x, I have written it as psi over here. Okay, and then u infinity l as it is. Okay, I hope this is understood. Let us come to the third question now, which is a numerical one, and in this example we will understand the velocity pressure decoupling problem which exists on a collocated grid. As I had explained in the theory session, we have something called a velocity pressure decoupling problem when we use a collocated grid. Okay, that we will try to understand with this particular problem. Although this is not an exact problem to understand that, but anyway we can try to analyze it. Okay, so in a non-dimensional 1D pressure distribution given by P of I is equal to 50, P of I plus 1 is equal to 80, P of I minus 1 also equal to 80, I plus 250, I minus 250 with grid spacing so and so. Pressure gradient at a point I needs to be calculated on a collocated grid. Okay. We will try to solve it together. Okay. Now we have a one-dimensional domain. Okay, we have I. Okay, we have I plus 1, we have I minus 1. Okay, and we have I plus 2, I minus 2. Okay, so first of all, tell me where does dp by dx term comes into picture? Like in which equation does dp by dx come into picture? Can you write on the chat box? In which equation does dp by dx come into picture? Okay, yes, exactly, momentum x momentum equation. Okay, so in that particular equation we get dp by dx. Okay, now if we are considering a collocated grid or a non-staggered grid, what it means is that all the variables are stored at only one particular point of the grid. So if we take velocity, pressure, both are stored for I at this particular point only, which I have marked cross marked here, I. Okay, both velocity, okay, and pressure are stored at this particular point only. So when we come up with the x momentum equation, we get this dp by dx at I. Okay, so what does that mean? So dp by dx at I, so here you have the west face and here you have the east face. Okay, so dou p by dou x at this particular I, how can you write it? Dou p by dou x at I, how can you write it? Using a central difference scheme. Okay, can you write down on the chat box how we can write dou p by dou x using a central difference scheme at this particular point I? Yes, exactly. PE minus PW divided by delta x. Okay, XE minus XW, that is delta x. Okay, now how can we write PE? We can just do a linear interpolation, that is PI plus PI plus 1 divided by 2. Similarly, for PW, we can write PI minus 1 plus PI divided by 2. Okay, let me just sum it. Okay, 2 delta x, that is divided by 2, I have brought it into denominator. PE, I can write PI plus 1 plus PI. Okay, you have then minus, what is that? PW, that we can write again at PI plus PI minus 1. Okay, now you will observe that this pi itself will get cancelled out. Okay, so that is why it is called as pressure velocity decoupling. Okay, pi will not come into picture. Okay, so whereas you are doing everything on the ith grid point, you are solving the x momentum on the ith grid point, so ideally you should get pi, right? But you are not getting that when you do this equation. So that is what is called as pressure velocity decoupling. The velocity is mainly decoupled with the pressure. Okay, so ultimately you get pi plus 1 minus pi minus 1 divided by 2 delta x. Okay, so if we particularly see this example, what would be that value? Pi plus 1 minus pi minus 1 divided by 2 delta x. Can you write down on the chat box? We have here as 50, I plus 1 80, again 50. Okay, here we have I minus 1 80 and this is 50. What should be the value of dp by dx at I then? The numerical value. Can you write down on the chat box? We have derived the equation here. It should be pi plus 1 minus pi minus 1 divided by 2 delta x. Pi plus 1 is 80. Pi minus 1 is 80. So this will basically become 0. Okay, dp by dx at I will become 0. No, not 130. See, here we are getting pi plus 1 minus pi minus 1. Okay, from this equation, I hope that is understood. Okay, pi plus 1 minus pi minus 1. If you see the values, pi plus 1 also it is 80, pi minus 1 also it is 80. Okay, 50 is at I, but I itself has got deleted here. Okay, so it will become 0. Okay, I hope that is clear. Okay, 80 minus 80 divided by 2 delta x, so it is 0. But if you see the pressure distribution in this particular grid, it is 50, 80, 50, 80. So definitely if you plot this, it is somehow something like this sinusoidal curve. So how can you tell that the pressure gradient is 0 in this particular grid? Pressure gradient should not be equal to 0 in ideally condition. Okay, because if you have some variation in pressure, right, across the length, that is not being considered by this particular kind of collocated grid, should not be equal to 0. But it turns out that when we use this collocated grid, it comes out to be 0. And this can have this can have serious issues when you numerically implement it. Okay, so you are getting a pressure gradient, it is turning out to be 0. 80 minus 80 divided by 2 delta x, it is coming out to be 0. But if you see actual variation of dp by dx, it is something like this sinusoidal curve. You have somewhere you have 50, you have 80, and then again going to 50. Okay, so if you see this graph, the pressure gradient should not be equal to 0, but with the use of collocated grid or a non-staggered grid, you are getting that to be equal to 0. So that is the necessity why we have to go with a staggered grid. Okay, so this problem has indicated us the necessity for using a staggered grid. Okay, I have solved it again here on the paper itself, which I solved on the clipboard just now. Okay, so if we see it, we will get 80 plus 50 minus again 80 plus 50 divided by 2 delta x, which is go to 0. Okay, so now let us try to understand how a staggered grid will solve the same problem. Okay, now in the question number 4 we will consider a staggered grid. Okay, fine. So here the fourth question is based on staggered grid arrangement. Okay, so a non-dimensional 2D pressure distribution is given in the following figure. Okay, so they have given the pressure at 4 different grid points. But what they say is that for a staggered grid, the dp by dx for calculating u at I plus half, please note this, okay, it is I plus half comma j. That is where we are storing the velocity in a staggered grid. As I told earlier also, on the east face, we are storing the velocity. We are making the control volume on the east face of this main control volume. Okay, I'll indicate it through figures. Okay, then you will clearly understand it. And calculate dp by dy for the y velocity control volume, which is on the north face. Okay, that is, it is denoted by I comma j plus half. Okay, so let us try to see how this kind of works out. Now let us come to the first part. Okay, that is calculation of dp by dx. Okay, so this is I comma j, you have I plus 1 comma j, and you have I plus half in between. Okay, I plus half comma j. Now you have to calculate the uh, value of dp by dx, which comes in x momentum equation for velocity, and velocity is stored in this east phase. So this is actual control volume, which I'll draw with a solid line. Okay, solid line, I'll draw the x actual control volume, but here it is only for pressure. Okay, this solid line is for pressure. Now the control volume which we consider for the x velocity is this dotted lines. Okay, this dotted line indicates the control volume for the x velocity. Okay, so it is centered around this point I plus half comma j. So that is why in the question it is asked, find the dp by dx, okay, at I plus half comma j, okay, for x velocity. momentum equation, x momentum equation. So again here, if we see dp by dx, what should it be? If I write it as O, which is there in that question itself, okay, I will write it as E, and let me just write it as P for present control volume, x momentum. So what should be dp by dx now? Similar to the way in which we did earlier, can you write down on the chat box, please? What should be the dp by dx now at this particular I plus half comma j in terms of this O, E and P? How can you write it? This distance will be delta x. Okay, can you write down on the chat box? Yes, it should be PE minus PO divided by delta x. Good. So what is that? Pi plus 1 comma j minus P of I comma j. Okay, P of I plus 1 comma j minus P of I comma j divided by delta x. Now you will see the value. What should be the value? 200 minus 220 divided by what is the delta x? 0.1. So what should it be then? What should be the value? 220 minus 200. Okay, sorry, 200 minus 220. 200 minus 220 divided by 0.1. What should be the answer? So it is 20 divided by 0.1. So it should be minus 200, right? dp by dx. Is that correct? dp by dx should be minus 200. Okay, let us see dp by dy. I'll just give a hint. I want you guys to uh, uh, calculate dp by dy similarly. Okay, so now we have this particular orientation. We have O here. Okay, we have the n, north control volume. In between we store the velocity for y. Okay, that is I comma j plus half. That is why it is called j plus half, and this is I comma j. This is I comma j plus 1. Now dp by dy, which comes in y momentum. Okay, so for that the control volume will be this dashed line again, as I did for x momentum control volume. Okay, this solid line will be for the pressure, similar to the previous case. Now what should be dp by dy? I'll write the values also. Maybe you can just write the answer on the chat box. 180, 220. What should be the answer? Here 180 it is, here 220 it is. Oh, yeah, it should be 180 minus 220 divided by 1, which comes out 40 divided by 1. It should be 400. Yes, correct. Minus 400. Okay. So yes, so this should be the answer. So now you can see that although in this problem here it was different, again 260 was there. Okay, let me do one thing. Let us take the S control volume also. Okay, now assume that you had 180 only here. Okay, you had 180 only, you had 180, 220, 180. Now if you had taken just a collocated grid, similar to the problem which we discussed above here. Okay, we had the sinusoidal type of variation. Same thing if we have here in the y direction, the dp by dy would have become 0 if we have taken collocated grid. But you can see the magic which is happening now. Okay, when we take this staggered grid, the dp by dy is coming out to be a non-zero value. Okay, if we do the same problem with a collocated grid, dp by dy will become 0 in a collocated grid. But actually that's not the case, because there is a sinusoidal variation in the pressure. Okay, so this is correct with what we calculated with staggered grid. So I hope that this gives a clear understanding of why we have to use a staggered grid, because that is the main aspect in CFD according to me. Okay, if you don't know why you are using staggered grid, you will face lot of issues when you are implementing it. Okay, when you understand the background behind using some particular method, then you will be much more confident while using the method. Okay, so I hope that this gives a clear indication of why we are using a, staggered grid. Okay, so yeah, so minus 200 for x, dp by dx, and minus 400 for dp by dy. So let us see the last question of today's tutorial session. Okay, so whenever we deal with computational fluid dynamics, okay, so we have one more issue which I might have forgot. Okay, so you have, okay, domain something like this, and if you divide it into control volumes, okay, so you have this centroid of the control volumes. Near the boundary they will be like this, and in the internal also they will be the same. But you have some boundary points also which I am marking by this cross marks. Okay, so at all the other points you have the distance to be delta x. Okay, which is same for internal grid points. Now when we come to the boundary, you notice that the distance here becomes half of delta x. Okay, so this point you have to be very careful when you are deriving the linear algebraic equation for the border grid point. So this is usually termed as border grid point, which is close to the boundary, which is next to the boundary, is called as border grid point. Because anyway for boundary grid point you are not doing LAE, that is linear algebraic equations, so you need not worry about boundary. But when you come to this border grid points you have to be careful. Okay, so that is why this question is framed, the fifth question. Okay, the U control volume is located next to the solid wall. Okay, this is a solid wall and we have a zero velocity on the solid wall. We all know that. The non-dimensional U component of velocity next to this solid wall ui comma 1 is given as 0.03. What should be the value of du by dy at S? That is at this boundary, what should be the value of du by dl? Can you try to solve it and write the answer? See, I'll just write the problem here. You have at this particular u of I comma 1, you have some velocity. Okay, what is that velocity? 0.03. You want to calculate at this boundary else what should be the du by dy at S. Can you write the answer on the chat box? At least in the fraction format. Okay, and this is delta y by 2, the distance. I think it is 5 mm, so 2.5 mm delta y by 2. Yes, let us try to see that. Okay, so du by dy, if we do forward differencing, because we cannot do central differencing because we do not have point next to this. Yes, so if we do this, u of I comma 1 minus u at S, that is 0, divided by 2.5 mm, 2.5 into 10 raised to minus 3. So this will be 0.03 divided by 2.5 into 10 raised to 3, that is around how much, 30 divided by 2.5. Yeah, this is 5 divided by 2, 6. Yeah, it should be 12. Yes, correct. 6 to the 12. Yeah, so correct. Good. So these were the questions which I wanted to discuss today. Okay, so if you have any queries you can ask. Okay, so otherwise you can leave the meeting, and if you have any feedback which you want to give also, you can give that feedback. Okay, Also, in this PowerPoint presentation, which I will be attaching in the Google Drive, I have attached two links wherein in one of the link it is beautifully explained what is the difference between a incompressible fluid and an incompressible flow. Okay, so you can go through this link and see what is the difference. And in the first link, the difference between a conservative and a non-conservative form through a physical perspective it is explained. Mathematically we can understand that very easily, but we also have to understand some things with a physical perspective that gives a better understanding. Okay, staggered grid is not simple to understand. See, did you understand the necessity for taking staggered grid to this using the two problems which we discussed? Can you write down on the chat box? Otherwise, I'll allow you to speak. To Okay, maybe you can unmute and speak also. Okay. Did you understand the necessity for taking staggered grid first of all? No, staggered grid is two dimensional. I mean 2D or 3D, wherever, 1D, 2D or 3D, everywhere it can be applied. Okay. So, did you understand the necessity for taking the staggered grid? Because we discussed two problems, right? With one with collocated grid and one with staggered grid, and saw what was the difference which was happening with respect to the pressure gradient. So, once you understand the necessity, you can understand the staggered grid in a much better form. Okay. So, what we have is this whole domain. Just for simplicity, I will divide it into 3 cross 3 control volumes. Okay. Yeah, exactly. If we have some flows wherein the flow is very pulsatile in nature, we have oscillations in pressure. So in that time, the pressure distribution might look something like this. But this is in actual reality. But if we use the numerical schemes, it might make it zero. If we use a collocated grid, okay, it might make it zero. Okay, and then we might end up although the equations satisfy this discretization scheme, the physical reality and the numerical results are far away. Okay, zero we get. This is not exactly this, right? But this also satisfies the equation. Okay, the Navier-Stokes equation. But it is far away from the reality. So that is why we have to use the staggered grid. Yes, to capture the oscillations in the pressure. Okay, so the way in which we do is that, see, this is our control volume, this box, square box or rectangle, whatever. So at the centroid we have a grid point. Okay, so there usually what we do is we store all the value of the variables. Okay, u, v, p. If three dimension, we take w also at this particular point only, at the centroid. Okay, that is in a collocated grid. But to avoid this pressure velocity decoupling, what we do is that we store only p here. Okay, this is the control volume for p now. Okay, the solid lines whichever are there. Now what we do is that since we need the pressure gradient at the faces, we make this centroid only as a face. The next centroid will come at E. Okay, so for x momentum I want at east face and west face. So I'll make this only as face. Okay, that is done by storing the velocity at the face, okay, of this control volume, and defining a new control volume for a x velocity, which is I'll indicate by the solid lines. Okay, so this is how I define the storage of new x velocity. Okay, it's everything to do with the storage only. Okay, similarly we do for y. Okay, we store the y v at this north face, so that when we go d p by dy, we need at the north face and the south face. So I'll make these centroids only as the north face by making a different control volume. Okay, so yeah, okay, I hope that is understood. That is the way in which we go about. Okay, so we store it at different points. Okay, so if there are no other queries, you can leave the meeting. Thanks for attending. Okay.